what's the probability of it of your system transitioning to state UM in a given time period, or per unit time, let's say. So you just divide this whole thing by t, and you call that rate, let's say W. So it'll just be pi, h bar squared rho divide. And I put that in a bracket. That is Fermi's golden rule. Right? It's the rate at which your system transitions to state M from your K. Seems kind of puzzling. It sounds as though there's just one K. It just goes against. Look, I'm finding this whole, these last couple of sessions not clear, not well expressed. That's just my feeling. Anyway. All right. So now Fermi's golden rule will get be much better treated in greater detail at graduate level. So if you're feeling somewhat fuzzy at this overview, that's probably not surprising. Alright, so now you may ask why a golden rule. I assume it's because it's used in many applications. Well, the text does say this. This Fermi's golden rule has a wide range of applications. It gets used a lot, so in a sense maybe worth its weight in gold. So, Fermi's golden rule. Somebody did a bit of marketing, I suppose, at some stage. All right. So next topic is so double line here. So you're emitting and absorbing electromagnetic radiation by atoms. So your atom is emitting and absorbing electromagnetic waves. That's the next topic. Right? Now, to do that properly in real detail, you can't do that at undergrad level. You need to know how to quantize electromagnetic fields. So that's the topic of quantum field theory, and you're talking interaction of quantized electromagnetic fields, quantum field theory, with atoms, and that's what QED is all about. That's quantum electrodynamics. Okay, so these are both graduate level topics, and we will do these in time, but you'll see they're a lot harder. But still, in this particular case, you can still get some correct results using a sort of quasi-classical approach to your perturbation. Your H dashed is you can approximate your H dashed as a classical perturbation, right? So here's an example of doing that kind of thing. So sort of arguing reasonably classically in a sense. Okay. So an electromagnetic wave. Think electromagnetic theory, classical electromagnetic theory of Maxwell, and so an electromagnetic wave is just an oscillating an electric field, let's say. Well, strictly, if the electric field's oscillating this way, and the magnetic field's oscillating that way. But let's concentrate on the electric field, and let's say that the particle, the atom, that the electromagnetic wave is acting on, perturbing, is barely moving. So its velocity v is pretty well zero, and hence the magnetic field will have a negligible impact on that atom. Right? That comes out of electromagnetic theory. The magnetic force on a charge depends partly on its velocity, the charge's velocity. Yeah. Well, anyway, so let's just concentrate then on the electric field, okay, and assume that the wavelength of this oscillating field is much larger, much larger than the size of the atom. So in other words, you don't have to worry about E varying over the size of the atom. You just effectively call it a constant. So let's just call it E naught, right? Now it's oscillating, so you'll have some sort of oscillatory term. So let's just call it cos omega t. So it's your angular frequency, omega t. So this is your perturbing electromagnetic wave. Okay. Let's say it's of this form, and effectively your E naught, just treat that as a constant, right? So the perturbing, your H dashed, will be a function of this energy E. Now let's say, let's keep things simple. Let's say we've got one atom, one electron in your atom, and so we're talking about the perturbation on that atom. Sorry, that electron. Okay, the electron charge minus E. So your potential energy then will be of this sort of form. So here your minus E, little e, the charge on the electron. Big E, that's the perturbing electromagnetic field. That's this. So you could have that as vectors. So E dot R. That's like little e, big E is a force. The force on the electron due to the presence of the electromagnetic field, E. So that's a force times a distance, and it gives you work. That's the definition of work, force applied over a distance. So that work, energy, so that would be your perturbing term, your H dashed. Okay? Now we can apply the theory. So hold on. So we have a harmonic perturbation, right? So due to this. So in other words, your H bar is of this form. Okay? That's your H bar, which is this. Okay, and that means we can apply the theory. We talked about harmonic perturbations in a few sessions back, so we can apply that theory to this particular problem, right? So now we've calculated the probability, transition probability from, this whole chapter is on transitions, right? The transition from state K to state M. So it's from state K to state M under this perturbation. So you've got H bar is this. So we can plug this H into the formula that we've been deriving and calculate the AM squared as the probability of the transition from state K to state M. Now that'll be the next session. Right, so I'll just go straight on in the next session.